Hello friends and welcome back to yet another session of Target JEE Advanced brought to you by the team here at Byju's. Today we are going to look at a chapter in mathematics which is probability. The moment we say probability, a lot of students are a little disillusioned because this chapter is an Achilles heel to a lot of you, because this chapter has questions that will always stump you in the examination. So today we are going to quickly analyze probability from the examination point of view and then look at some of these twisted, tricky, logical questions which come from probability. So how important is probability from the examination point of view? Well, in fact, probability always fetches questions in the exam. If you look at the main examination, the last 6 or 7 years, every year inevitably one question has come from probability. Year 2017 was a special year because there were some papers where 2 questions came from probability in the examination. Apart from that, every year in every paper there'll be just 1 question from probability. A lot of these questions tend to be from general probability. These are like logical questions, and even without knowing the concepts of probability in detail, you will be actually able to solve some of these questions if your logical thinking ability is pretty strong. Well, let's quickly look at the different sections of this chapter from which questions generally came in the main examination. In 2013, the question was from general probability. It was not from any specific section as such. Whereas in 2014, the concept of independent events was tested in the examination. 2015, the question which came was from probability distribution, the only distribution that you learn in probability in your 11th and 12th standard. That was tested in the 2015 examination. 2016 again tested your understanding of independent events. And in 2017, they tested probability questions. There were 2 questions, remember, and you are using the concepts of sets and permutations and combinations. So probability using the concepts of sets and permutations and combinations is what was asked in Main 2017. 2018 was a year when conditional probability found application in the question papers. Different papers and different questions, but predominantly these questions tended to be from the concept of conditional probability. And in the questions of 2019, again 1 question, conditional probability was sometimes tested, Bayes' theorem was sometimes tested. So again, mostly conditional probability was what was focused on in the different papers of 2019. Now let's look at the advanced examination. Now, unlike the main examination, advanced examination does not always fetch 1 question, but it fetches more than 1 question. So probability is an important section in the advanced examination. If you look at the last few years, every year more than 1 question has come. In 2013, there were 4 questions. Remember, for 2013 was a year when probability had a lot of weightage in the examination. 4 questions, 1 of them was a multiple correct answer type of question. One of them was an integer type of question, and 2 passage questions. A passage followed by 2 questions were asked from probability. A lot of weightage to that, and different concepts were tested. The concepts of independent event, the concept of conditional probability, all of these were tested in these different questions. And of course, general probability is always tested. You need to know some logical thinking in order to solve probability questions inevitably. 2013 was a year when 4 questions came. Then 2014 was a year when 3 questions came. One was a single correct answer type of question. Another was a comprehension type of question. There was a passage and there were 2 questions following the passage. So that was a comprehension type of question, and both these questions generally tested the concepts of conditional probability, though of course a little bit of logical thinking was also needed to solve these questions. In 2015, we had 3 questions. Again, a comprehension question, a passage followed by 2 questions, and 1 question which was an integer type of question. This year, the integer type of question was a probability distribution question, and the comprehension questions generally tested you on conditional probability. And of course, as always, general probability and your logical thinking skills were definitely put to use when these questions had to be solved. 2016 was a year which again saw 3 questions, a comprehension passage with 2 questions which followed, and a single correct answer type of question, this time from Bayes' theorem. The passage was based again on conditional probability. So you see, conditional probability and Bayes' theorem, these are really important concepts from this particular chapter. 2017 saw a small decrease in the number of questions. We just had 2 questions. One was a single correct answer type of question and one was a multiple correct answer type of questions. And these questions came from, again, conditional probability and PNC based probability. So again, you see conditional probability is an important concept. Finally, the last year in 2018, we again had 2 questions. Both of these were comprehension passage questions, questions which followed a passage. So again, passages are very normal in the advanced examination for probability. You see, the probability of getting a passage type of question from probability is actually very high in the advanced examination. The chapters, the concepts of probability which were tested in 2018 were the principle of inclusion and exclusion. So probability is a very important chapter from the exam point of view, especially in the advanced examination, because more than one question comes in that paper from probability. Now, different concepts of probability are very important, but it's most important to logically think when it comes to probability. I'm going to solve a few questions for you and you will see for yourself how important logical thinking is for probability. In this question, there is a letter which is known to have arrived from either Tatanagar or Calcutta. All that can be seen on the envelope which contained this particular letter are 2 consecutive letters T and A of the English alphabet. Now, the objective in this question is to find out the probability that this letter has arrived from Calcutta. So how do you solve this question? Well, this is a typical Bayes theorem question. That should be enough clue for you to actually go and solve this question. But let me show how it is done. So if we did not have this piece of information that T and A, 2 consecutive letters, are visible on the envelope, then we know that the probability that the letter would have arrived from Tatanagar or Calcutta would have been half, because we know that it has arrived from one of these cities. So it would have been equally likely that it would have come from Calcutta or Tatanagar. So I'm going to say T as the event that the letter has arrived from Tatanagar and C as the event that the letter has arrived from Calcutta. So P of T would have been 1/2 and P of C also would have been 1/2 in case we did not have that additional piece of information. Now, TA is visible on the envelope. What is the probability that TA is visible given that the letter has come from Tatanagar? Well, consecutive letters. Well, there are 9 letters in Tatanagar, which means you have 8 pairs of consecutive letters, isn't it? There is TA, AT, TA, AN, so on all the way till AR. These are the 8 pairs of consecutive letters that you can form from Tatanagar. So the probability that TA appears given that the letter is from Tatanagar is going to be 2 divided by 8, because Tatanagar has 2 pairs of TA appearing in it, and in total it has 8 consecutive letter pairs. So the probability that TA is visible and the letter has come from Tatanagar is 2/8. Similarly, the probability that TA is visible and the letter has come from Calcutta would be 1/7, because Calcutta has only 1 TA, and because Calcutta has 8 letters, you can form 7 consecutive pairs of letters from Calcutta. So the probability that TA appears given that it's come from Calcutta is 1/7. Now we have all the information required to go forward and use Bayes theorem to identify that the probability of letter coming from Calcutta, given that we know TA appears on the envelope. So the probability the letter has come from Calcutta given TA appears, well, this will be nothing but the probability that TA appears given the letter has come from Kolkata multiplied by probability that the letter has come from Calcutta divided by the same thing, probability that TA appears given the letter has come from Calcutta into probability of Calcutta, plus the probability that TA appears and the letter is said to have come from Tatanagar into the probability of Tatanagar. Well, this was straightforward Bayes theorem. We just needed to identify the required elements that have to be put into this Bayes theorem formula. Well, we did that, and from here on it's pretty straightforward to compute. So the probability that the letter has come from Calcutta given TA appears, well, this is going to be nothing but 1/7 into 1/2 divided by 1 by 7 into 1 by 2 plus 2 by 8 into 1 by 2. I can cancel out all the halves. So then I'm going to get 1 by 7 divided by 1 by 7 plus 1 by 4. This is all about a simple calculation using fractions. 1 by 7 divided by, you have 11 by 4 into 7. I cancel out the 7s and the answer will be 4 by 11. So the probability that the letter has come from Calcutta, given that TA appears in the envelope, is actually 4 divided by 11. If you work out, you would have seen that the probability of the letter coming from Tata Nagar, given TA appears on the envelope, would have been the complement of this, which would have been actually 7 over 11. Very simple question, very simple application of Bayes theorem question. There was nothing fancy in this question at all. You just needed to identify that this is a Bayes theorem question. In this question, we've been given that A and B are two independent events. Further, a few pieces of information have been given. The probability that the complement of A intersection B happens is 2 by 15. And the probability of A intersection the complement of B, that's 1 by 6. The objective in this question is to find out the probability of A. Well, this seems like a very simple question, but it has a small bit of information that you must actually pay a lot of attention to. We know that if A and B are two independent events, then the probability of A intersection B will be simply probability of A into probability of B. But in both the pieces of information that are given to us, we don't have A intersection B. We have A complement intersection B and A intersection B complement. Now, does this rule hold if we have complements of an event? In fact, that's the crucial bit in this particular question. It does hold, because whether A happens or not does not affect B. So the complement of A happening or not will also not affect B, because these are independent events. So A happens or not, B is not affected. B happens or not, A is not affected. Similarly, A not happening, which means the complement of A happens, does not affect B, because A and B are independent events. So this means that when you have independent events, complements also behave in the same way like the events itself. So probability of A complement B intersection B will be nothing but probability of A complement multiplied by the probability of B, because A and B are independent events. Similarly, probability of A intersection B complement will be probability of A into probability of B complement. So we actually have a couple of equations here, and we need to solve for two variables, so that's going to be very simple. So let's do a little bit of mathematical manipulation here, because we know what is probability of A complement. That's nothing but 1 minus probability of A. This is going to be multiplied by probability of B, and we know that this is equal to 2 over 15. Similarly, probability of A into 1 minus probability of B will be equal to 1 over 6. The objective is to find the probability of A. I'm going to call it just a P, a small p, because I don't want to keep writing capital P of A all the time during my calculation. So I'm going to call P of A, the probability of event A, as my small letter p, which is what I have to find out. So what I have is 1 minus P into P of B is 2 by 15. So I can say the probability of B as 2 by 15 into 1 upon 1 minus P. So that's P of B, and I'm going to substitute P of B in my second equation, and from there I'm definitely going to get a quadratic in terms of P of A and solve for that. So what I have is I have P of A, which is small p, into 1 minus P of B. Well, P of B is 2 divided by 15, and in the denominator you also have 1 minus P, and this is equal to 1 over 6. So what we get is P multiplied by 15 times 1 minus P minus 2 divided by 15 times 1 minus P to be equal to 1 over 6. Let's do a little bit of simplification. This 6 cancels with the 15, so you get 2 here and a 5 here. So what you actually have is a 15 minus 2 in the numerator. That's going to give you a 13. So you have 13p minus 15p square all multiplied by 2 to be equal to 5 minus 5p. So you have 26p on the left hand side, a negative 5p on the right hand side. So a total of 31p on the left hand side minus you have 15 into 2p square, that will be 30p square to be equal to 5. Let's bring everything on to the right hand side and then let's solve that equation. So you have 30p square minus 31p plus 5 to be equal to 0. You have to solve this quadratic equation to get the value of a small p, which is nothing but the probability of event A. So 30 into 5 is 150. 150 can be factorized as 25 times 6, and 25 plus 6 is 31, or minus 25 minus 6 is minus 31. That's the factorization for this. So I'm going to write minus 31p as minus 25p minus 6p and then do the factorization. I can take a 5p common out and then I get a 6p minus 5, and then if I take a minus 1 common out, I again get a 6p minus 5 to be equal to 0. So I get the value of p to be equal to 1 by 5 or p to be equal to 5 by 6. Both these are admissible values for probability of A because both of them are actually less than 1. So the correct answers for probability of A are 1 by 5 and 5 by 6. So if you want, you can actually find out the probability of B as well, because probability of B is nothing but 2/15 of 1 divided by 1 minus probability of A. Plug in these two values and you would have gotten the probability of B as well. So irrespective of whether probability of A is asked or B is asked, that's not the crux of this question, because the crux of this question is identifying that A complement and B complement also behave in the same way as A and B when A and B are independent event. That is where the crux of this question lay. Next, we're going to look at a passage type of question. So there's a passage given and two questions follow. The passage has this particular information here. We have three boxes, B1, B2 and B3, and these three boxes have different numbers of white, red and black balls. So box 1 has 1 white, 2 black and 3 red balls, a total of 6 balls there. Box 2 has 2 whites, 3 reds and 4 black balls, a total of 9 balls there. And box 3 has 3 whites, 4 red and 5 black balls, a total of 12 balls there. Now in question 1, we've been told that one ball is drawn from each of these boxes, and the objective is to find out the probability that all 3 balls are of the same color. This is a very straightforward and simple question. Actually nothing much complicated here. So we have to find out that the probability of the fact that all the balls are the same color. So we can get all the balls to be white, all the balls to be red, or all the balls to be black. That's what we have to find out. We have to find out the probability of white, white, white plus the probability of red, red, red plus the probability of black, black, black. This is what we have to find out. So now the probability of drawing white from the first box, that's independent of drawing white from the second and the third. So all these will be independent events. So the probability of white, white, white will be probability of white from box 1 multiplied by probability of white from box 2 multiplied by probability of white from box 3. And that same logic will apply for the reds as well as for the blacks. So what is the probability of white from box 1? Well, that's going to be 1 divided by 6. Probability of white from box 2, that's going to be 2 divided by 9, and the probability of white from box 3 is 3 divided by 12. The next thing is red, that's going to be 3 divided by 6 into 3 divided by 9 into 4 divided by 12. And for the blacks, it's going to be 2 by 6 into 4 by 9, and the third one will be 5 by 12. Well, you have a common denominator already, 6 into 9 into 12. Well, 6 into 9 into 12, well, 12 9s are 108 into 6 will be 648. So you have a common denominator of 648. The first term is 6, the next term is 9 4s are 36, and the last term is going to be 22s are 40. So it's 6 plus 36 plus 40, that's 42 plus 40 are 82. 82 divided by 648. So the probability that all balls are all of the same color will be nothing but 82 over 648. So the probability of all balls of same color, that's nothing but 82 divided by 648. In fact, this can be simplified. If you want, you could have written it as 41 divided by 324. But look at the options. 41 divided by 324 doesn't exist in the options. The only option is 82 over 648. Single correct answer type of questions. So no simplification required. The correct answer is 82 over 648. Continuing on to the second part of this passage question, well, the second part has this particular information given. 2 balls have been drawn without replacement from a randomly chosen box. Now, it turns out that one of these balls is white and the other ball is red. We have to find out the probability that these 2 balls are drawn from box B2. Let's analyze the question. We have drawn 2 balls, and these 2 balls, we know their colors. We have to find out which box has this ball come from. A typical Bayes theorem question, because we can find out all the reverse probabilities. We can find out what is the probability that these 2 colored balls come from box 1, from box 2, from box 3. We can also find out what is the probability of randomly choosing a box. So given all these pieces of information, we can find out what is the probability that we know the color of 2 balls, that it has come from a particular box. Typical Bayes theorem question. So we're going to solve this using Bayes theorem. So 2 balls have been drawn without replacement, and 1 ball is white, 1 ball is red. So what is the probability that we get a white and a red ball from box 1? So what is the probability here? Well, we have only 1 white ball there, so that's going to be 1C1 multiplied by, we have 3 red balls, 3C1 divided by 6C2. Remember, we have to use combinations because it's without replacement. So we have to use combinations here. It'll be 1 into 3 divided by, well, 6C2. For those of you already know that, that'll be nothing but 15. But for those of you don't know, that'll be 6 into 5 divided by 2. So that's going to be a very simple simplification. So you will get the answer to be 1 divided by 5. So the probability of white and red, 1 white and 1 red, given that it's box 1, that's going to be 1 over 5. So now what is the probability that we have 1 white and 1 red given that it is box 2? Well, box 2 has 2 white balls and it has 3 red balls. So we have 2C1 into 3C1 and a total of 9 balls, so 9C2. Well, that's going to be 2 into 3 divided by, well, 9 into 8 divided by 2. That's 9C2 for you. Well, let's do some simplification here. Well, the thing turns out to be nothing but 1 over 6. Similarly, the probability that we have 1 red and 1 white ball given box 3. Box 3 has 3 whites and 4 reds. So this is going to be 3C1 into 4C1 divided by a total of 12 balls, 12C2. So we will get the answer here as 3 into 4 by 12 into 11 by 2. Again, 3 into 4 is 12, so that 12 cancels out and we end up with 2 over 11. Now, what is the probability of randomly choosing a box? We have 3 boxes and it's equally likely that you might choose one of the boxes. So the probability of box 1 is equal to the probability of choosing box 2, which is equal to the probability of choosing box 3, and that is equal to 1 over 3. So now we have all the information that is required to use Bayes theorem to find out the probability that we had chosen box 2 given that we had a white and a red ball. Well, that's going to be nothing but probability of white and red given B2, which is 1 over 6 multiplied by probability of B2 1 over 3 divided by it's the same thing, 1 over 6 into 1 over 3 plus you have to use a total probability theorem, so you have to find out the probability of white red given B1 into B1. White red given B1 was 1 by 5 and that is going to be multiplied by 1 by 3 plus probability of white red given B3, which is 2 by 11 into 1 by 3. So now I can actually cancel out all the 1/3 because we can take a 1/3 common out from the denominator. So we'll be left with 1 by 6, a common denominator of well, in this case 330, because 30 11s are 330, and then you need 55 plus 66 plus 32s are 60. So this will lead to a little bit of simplification. So you actually have 55 divided by 55 plus 66 is 121, plus 60 is 181. No more simplification required, because 55 by 181 appears in one of the options. You're going to map that option because it's a single correct answer. No need to do any simplification. I'm not even sure if you can do a simplification. So 55 by 181 is the correct answer to this question from the passage. So the first question from the passage was a very straightforward, simple one. The second one, you just had to identify it's a base theorem question. Then of course it was very simple as well. In this question, we've been given a biased coin. Remember, a biased coin does not have probability of head to be equal to half or the probability of tail to be equal to half. It will not be that case. So they've given us that the probability of head in this particular coin is some quantity P, and that quantity P is between 0 and 1. Wow, that wasn't great a piece of information, right? Because every probability has to lie between 0 and 1. The event which occurs is that the coin is repeatedly tossed till we get our first head. The moment we get our first head, we stop tossing the coin. Now we've been told that the probability that the number of tosses of the coin is even is equal to 2 by 5. So we have to now find out 3p. Well, it's an integer type of question, so in order to make the final answer an integer, they have given that 3p. The actual objective in this question is to find out p. Then you just multiply it by 3 and present an integer. That's what we're going to do in this particular question. We'll try and find out what that p is. So what is the event? The event is you go on tossing the coin and you stop when you get a head. The first time you get a head, you're going to stop. Now the probability of let's say we have r tosses of the coin before we get our first head. Well, that's going to be equal to, well, in all the previous tosses before the last one, we would have gotten tail. What's the probability of tail? The probability of tail is 1 minus p. So 1 minus p would have happened r minus 1 number of times, and then finally you would have gotten a head. So the probability of that would be p. Now our favorable outcome here is the number of tosses is even. So for that to happen, you could have gotten r to be equal to 2, or r to be equal to 4, or r to be equal to 6, and so on, and that would have gone on forever. So what is the probability of favorable outcome? Well, that is going to be equal to 2 by 5. So I'm going to call P of E, because of even number, as my favorable outcome, the probability of my favorable outcome. So probability of E will be equal to probability of R equal to 2 plus probability of R equal to 4 plus so on, R equal to 6, R equal to 8, and that is going to go on all the way up till infinity. So probability of E will be equal to, well, when r is equal to 2, you're going to get 1 minus p into p. That means the first toss is a tail and the second toss is a head. Then you have 1 minus p the whole cube, 3 tails and then a head into p, plus 1 minus p to the power 5 into p, and so on. So if you actually look at it, it's already a geometric progression wherein you are multiplying 1 minus p to each of 1 minus p the whole square to each of the preceding term, and then you're getting the new term. So it's actually a geometric series, and it's an infinite series, and the common difference is 1 minus p the whole square. Now 1 minus p is the probability of a tail, and that's going to be less than 1. So 1 minus p the whole square is definitely going to be less than 1. So it's an infinite geometric series with the common ratio to be actually less than 1. So we know the formula for that. So this is going to be equal to the first term, 1 minus p into p, divided by 1 minus, you have the common ratio, which is 1 minus p the whole square. And we know this is equal to, what is the value of that? That's 2 by 5. So this has been given to us. Now it's going to be simple calculation. So we have p minus p square multiplied by 5 to be equal to 2 times 1 minus 1 minus p square plus 2p. Well, 1 minus 1 will cancel out. So you actually have p's on both the sides. So I can cancel out certain p's because it's known that p is not equal to 0. So I can cancel out some of these p's from here. So eventually what I have is I have 5 minus 5p to be equal to negative 2p plus 4. So you do the manipulation in this particular case. So you get 1 to be equal to 3p, or p is 1/3, but that's not what is interesting. We are interested in finding 3p. 3p is 1. Well, that is the correct answer to this particular question. The correct answer to this integer type of question is 3p equal to 1. 1 is the right answer. 1 is what you will input at the end of solving this particular question. A very beautifully crafted question. So even if it's a biased coin, you really don't have to be worried, because we have equipped you well with the concepts of probability that will help you solve questions that have biased coins as well. Now this question has a little more information than other questions, so listen to it carefully. Mohan posts a letter to Sohan. Now the chances that Mohan's letter will reach Sohan is 9 out of 10 times. That means only 1 out of 10 times the letter will not reach Sohan. And every time Sohan receives a letter, he will definitely reply to that particular letter. So again, when Sohan writes a reply to Mohan, the same rule applies, that 1 out of 10 letters will not reach its destination. Now event A is nothing but the fact that Sohan receives the letter from Mohan, whereas event B is the fact that Mohan gets a reply from Sohan. Now this is a multiple correct answer kind of question, so we have to check which of the given options are correct. We'll have to individually go to each option and check them. The first option says P of B is 81 over 100, so we have to check if P of B is 81 over 100. But B is Mohan getting a reply. When will Mohan get a reply? Mohan will get a reply only after Sohan receives his letter. So P of B, so for the event B to happen, A should have already happened. So B is actually dependent on A. This piece of information is going to be handy, and it's going to be of use to you later on in this question as well. So remember that for event B to happen, A should have already occurred. So what is the probability that B will happen? Well, the probability that B will happen is the fact that first Sohan should receive a letter, and then Sohan writes a reply, which he inevitably always does. And then that letter should reach back to Mohan. So there are a lot of things which are happening, and they are sequential things. They don't happen in parallel. One happens, results in another, results in another. So the probability of those will be the product of all the three events. So initially, the probability of B will be the probability that Sohan receives the letter. Well, that's going to be 9 out of 10 times he's going to receive the letter. The probability that Sohan writes a reply, which is 1, he's always going to write a reply. And the probability that Mohan gets the letter, again 9 out of 10 letters will reach its destination, so it's going to be 9 out of 10. So the probability that Mohan gets a reply is going to be 81 over 100. So this is how you are going to find out the probability of B. And note that we've established the fact that B depends on A. Only after A happens, B will happen. So if Sohan receives a letter, only then he can write a reply, and Mohan will get the letter. So Mohan posting a letter is the first event, then Sohan receives the letter, then Sohan writes a reply, and then Mohan receives the letter. So what we see here is B is actually in some kind a subset of event A. So for event B to happen, A should have always occurred. Without A occurring, B will never happen. So in some sense, B is actually a subset of event A. Now that is going to be very crucial in our second option, because in the second option we have to find out what is the probability of A intersection B. And we've just established that B depends completely on A. For B to happen, A should have happened. And if A happens, there might be some cases where B might not happen, because Sohan might have received the letter, but the letter that he wrote back to Mohan, that might have not reached Mohan. That is possible. But if Mohan gets a reply, that means Sohan has definitely received Mohan's letter. So B is a subset of A in some sense. So P of A intersection B will be nothing but P of B, because B cannot happen in the absence of A, and that is actually equal to 81 by 100 itself. So this option is also correct. P of A intersection P equal to 81 by 100 is also correct. Now let's look at option C. Remember, it's a multiple select question, a multiple correct answer type of question. There are partial marks. So students who feel that they've already attempted this question for more time than required, they can stop here and go on to another question. If they don't want to continue, you will get partial marks. But of course, we always try to attempt the question in entirety, so we will try and solve this question completely. So now let's look at option C. So option C speaks about P of A given B complement. So this means that we have to find the probability that Sohan receives the letter given that Mohan has not received a reply. That's what is the English translation of this mathematical statement. So let's use the definition of conditional probability here. It's going to be P of A intersection B complement divided by P of B complement. Well, P of B complement is going to be very easy because we know P of B is 81 over 100. So P of B complement will be simply 19 over 100. Now we have to find out what is P of A intersection B complement. So what is B complement? B complement is the fact that Mohan does not receive a reply. So Mohan does not receive a reply after he's written a letter. Well, that happens, first he writes a letter 9 out of 10 times. That reaches Sohan and he inevitably writes a reply, and the letter has not reached Mohan, which means there is 1 out of 10 times when the letter will not reach Mohan. So the probability of A intersection B complement is actually the probability of B complement itself, which is 9/10 into 1/10, which is 9 over 100. I can cancel out the hundreds from the denominators of both the numerator and the denominator, and I get the answer of 9 over 19. All this works because event B depends completely on event A. B will never happen in isolation. B will happen only if A happens. Okay. So the final part is P of A union B. Now it's a well-established fact that B is completely dependent on A. So P of A union B will be nothing but P of A itself, because we have to see the probability of either A happening or B happening. So that will be nothing but P of A itself, because B will not happen if A does not happen. So it's going to be P of A itself, which is nothing but 9 over 10. So what we see in this particular question is all the 4 options are actually correct. So this multiple correct answer type of question has all 4 options to be correct. This question requires some amount of thought. It's not a question where you can simply put in formulae and solve. That's generally the trend with a lot of probability questions. You have to put in a lot of thought into these questions. So that's why probability is more or less an Achilles heel to a lot of students, because even if you solve n different varieties of question, it's not very difficult to form an n+1th type of question and stump you completely. So hope that you find a question which is something that you can easily attempt and solve. So we will solve one more question, and here is that last question. Now in this question, a lot of information is given, and you have to actually pay a lot of attention to how the question is being described. a coin is tossed, and based on the outcome of the coin, different things are done. If we get a head, a fair die is rolled 3 times. If we get a tail, a biased die is going to be rolled 3 times. Now this biased die has the property that the probability of getting an even number with this die is going to be 2 times the probability of getting an odd number. Now suppose we get n1, n2, n3 as the outcome from the 3 rolls of the dice. Now this n1, n2, n3 are such that iota to the power n1 plus iota to the power n2 plus iota to the power n3 is equal to 1. Okay, so that's my outcome n1, n2, n3. We know that. Now the objective in this question is to find the probability that we got this n1, n2, n3 to satisfy this property with the throw of a fair die. What is the probability that a fair die was used to obtain n1, n2, n3 such that that iota to the power n1 plus iota to the power n2 plus iota to the power n3 equal to 1 was satisfied? Rather tricky and interesting question. Eventually it will be a base theorem sort of a question, but to arrive there a lot of information is needed. So let's try and find out all the pieces of information. So what is the thing that we have to find out? Well, we have to find out the probability of a fair die given n1, n2, n3 will they satisfy the event. Okay, so we need to find this out. So using base theorem, well, this will be equal to the probability that n1, n2, n3 satisfies that event. I'm going to write it in this way. n1, n2, n3 satisfies the event that happened with the throw of the fair die into the probability of throwing a fair die divided by, well, the same thing, probability that n1, n2, n3 satisfy the event given a fair die was thrown, multiplied by the probability of fair die plus a probability that n1, n2, n3 well, they satisfy the event with the biased die, and then the probability that a biased die is thrown. Now we know P of F and P of B in this case, well, that is equal to half, because the coin which was tossed, which decided whether a biased die is being rolled or a fair die is being rolled, that was a fair coin, and the heads or tails has a probability of half. So we know this and we know this. Now we actually need to find out these two guys, and that's going to be a little tricky. So let's try and get to that. Okay, so first of all, what is the probability of getting different numbers on that biased die? Because we know that the probability of 1 equal to the probability of 2 equal to the probability of 3 all the way up to the probability of 6, which is equal to 1/6 for a fair die. But what about the biased die? Well, for the biased die, we know that the probability of getting a 1, 3 and 5, which is probability of getting an odd number, well, that is half of the probability of getting an even number. So 2 times the probability of getting 1, 3, 5 is the probability of getting 2, 4, 6. But we know that these two things actually add up to give a 1. Probability of getting 2, 4, 6 plus the probability of getting 1, 3, 5 adds up to give a 1. So I can write this as 1 minus the probability of getting 1, 3, 5, right? So if you solve this, you're going to get the probability of getting an odd number to be equal to 1/3, which means that the probability of getting an even number, well, that's going to be equal to 2/3. But we still don't know what is the probability of getting 1 or 2 or 3 or 4. We don't know the probability of individual numbers. And this is where a key assumption is going to be made in this question. Because this die is a biased die, we actually don't know whether the probability of 1, 3 and 5 are equally likely. We're going to assume that they are equally likely, because without that we cannot move ahead in this question. So I'm going to assume that 1, 3 and 5 have equal likelihood. So that would mean that probability of 1 is equal to probability of 3 equal to probability of 5, which will be equal to 1/9. Similar assumption for the even numbers gives me the probability of getting any of the even numbers as 2/9. So this is very crucial. If you don't make this assumption, there's no way this question can be solved, because it's a biased die. There is no way to say whether each of the even numbers or the odd numbers are equally likely, right? So we have found this. Now let's look at the event. N1, N2, N3 are the 3 outcomes, but they satisfy a condition. Iota to the power N1 plus iota to the power N2 plus iota to the power N3 is equal to 1. Now when can this happen? Now suppose iota to the power n1 is 1, iota to the power n2 is 1 and iota to the power n3 is -1. Of course, the sum will be this thing. Well, any different permutation combination of this is going to give you a sum of 1. But this is not the only case. There's one more case wherein if iota to the power n1 is iota and iota to the power n2 is negative iota, well, they cancel out. And then if iota to the power n3 is 1, we again get the sum to be equal to 1. So there are these two different cases. Now let's analyze the different situations when this can happen. Well, if n1 is equal to 4 and n2 is equal to 4, that's the only time when iota to the power n1 and iota to the power n2 will be 1 and 1 respectively. But for iota to the power n3 to be equal to negative 1, there are two cases for numbers n3 to be between 1 and 6. There are two cases which are 2 and 6. Of course, different permutations of this, we have to consider them. So we can have n1, n2, n3 to take different permutations of 442 or 446. Correct? Now 442 can be permuted in 3 factorial by 2 factorial ways or in 3 different ways, and 446 can be permuted again in 3 factorial by 2 factorial, which is nothing but again 3 different ways. Now let's find out the probability that n1, n2, n3 is 442 given we have a fair die. So if there's a fair die, the probability of this is going to be 1 by 6 into 1 by 6 into 1 by 6. Same with this case, 1 by 6 into 1 by 6 into 1 by 6. Well, if you add these two cases up and all of them having 3 different permutations possible, so you will actually get 6 times 1 by 6 into 1 by 6 into 1 by 6, which will be nothing but 1 by 36. So this is the case with the fair die. But what happens if you have the biased die? Well, if you have the biased die, then 446, well, 4 has a probability of 2 by 9. 4 again has a probability of 2 by 9 and 2 has a probability of 2 by 9 again. Same with the case of 6. It's going to be 2 by 9, 2 by 9 and 2 by 9. Again, 3 cases of these. So in all, I'll have 6 times 2 by 9 into 2 by 9 into 2 by 9. Well, let's do a little bit of simplification here. There's going to be a 2 and a 3 here, which will be nothing but 16 over 243. So with the biased die, if this is supposed to happen, that is n1, n2, n3 takes different permutations of 442 or 446, it can happen in 16 over 243 being its probability. Okay, now let's look at the other case when iota to the power n1 plus iota to the power n2 plus iota to the power n3 is equal to 1 because of iota to the power n1 being iota, the next term being negative iota and the next term being 1. Well, this can happen again in some different ways. Well, when you have iota, you can get iota if n1 is either 1 or 5. If n2 is equal to 3, that is the only time when iota to the power n2 will be equal to negative iota. And for n3 to be to give a value of iota to the power n3 equal to 1, n3 should be equal to 4. So again, you see these two different cases. N1, N2, N3 are 1, 3, 4 or 5, 3, 4. Well, again, different permutations of this. Well, these can be permuted in 3 factorial ways or in 6 ways. Both these can be permuted in 6 different ways. So now let's find out the probability of this happening with the fair die and the biased die. So if you have a fair die, things are very simple. 134 has a probability of 1/6 into 1/6 into 1/6, and the other thing also has a probability of 1/6 into 1/6 into 1/6. So we can actually take all this and multiply by 12, which is going to give you a value of 2 over 36. So with the biased die, things are going to be different. 1, 3, 4. There are 2 odd numbers and 1 even number. So that's going to have a probability of 1/9 into 1/9 into 2 by 9. And the other case also 2 odd numbers, 1 even number. So 1/9 into 1/9 into 2/9. So you can multiply all that by 12. So you're going to get a 4 here and a 3 here. So that's going to be nothing but 8 over 243. So now we actually are in a position where we can find out the probability that we know n1, n2, n3 satisfy the required event such that we have used the fair die. Well, when we have used the fair die, n1, n2, n3 will satisfy that event. Well, that is only possible for the probability of 1 by 36 plus 2 by 36. So that is 3 by 36 or 1 by 12. For the other case wherein n1, n2, n3, these things satisfy the event But with the biased coin, this is going to happen in 16 by 243 plus 8 by 243, which is nothing but a probability of 24 over 243. So now we are going to use Bayes' theorem. So the probability that a fair die was thrown such that n1, n2, n3, they satisfy our given event, that will be nothing but 1 by 12 into a half divided by 1 by 12 into a half plus 24 by 243 1 by 2. Okay, so now all my 1 by 2s are going to cancel out. 24 by 243, well, this can be simplified as 8 over 81. And now we can cancel out a 3 from here. You get a 4, 3 4s are, and 3 27s are. So this is going to be 1/4 divided by 27 plus 32 divided by 27 into 4. The 4s will cancel out, and eventually you will get an answer which is nothing but 27 divided by 59. So the correct answer to this rather very lengthy and very convoluted question is 27 over 59. A lot of intricate details were there in this question. There were concepts of permutations of and combinations as well in this particular question. Different cases had to be analyzed, and we actually had to deal with a biased die as well. So a very lengthy, convoluted question, and I just hope that such questions don't appear in your advanced examination, because it's challenging on multiple levels. It's challenging concept wise, and it's also very lengthy. So probability is a chapter which a lot of students find difficult in the examination, not because this is a chapter which is intense in terms of the concepts, but because there are no limit to the type of questions that can be formed and asked from this particular chapter. So even if you solve n different varieties of question, an n+1th question can stump you in the examinations. So try and solve a lot of questions in probability and hope that a question that you've already seen, a type of that question, appears in the examination. I hope you liked today's video, and I hope you've got a little bit of insight into the types of questions that come from probability. If you like our video, then please subscribe to this channel. Every time we make a new video, you will be notified about it. I will be back soon with yet another chapter and some more interesting questions that will help you in the preparation for the JEE examination. Till then, prepare well for the examination, and I'll see you very soon with yet another video.
For more videos and live lectures on the JEE, click on the subscribe button now.